Okay, welcome everyone to our lecture. Second hour. First hour was the review. Second hour is our Oscillations, chapter 15. I'm tired. Just to let you know, it's late and I'm probably, my handwriting is not so good at the moment. So let me start off with something about this whole topic. I don't know if I'll write out as much of this as I possibly can, but mostly this is verbal stuff. This chapter is deep. The ramifications are huge. It seems like it's not. It seems like it's really simple stuff, and it's just tedious mathematics and doing the integral or derivatives of sines and cosines, and it doesn't seem like it's going to be very interesting at all. But it deals with resonances. Resonances. And no, I haven't been drinking. Okay, so here's my thing. What resonates with you? That's my question. Will this physics lecture resonate with you? I don't know. Will this resonate with you? You're probably wondering, do I even see that mark right there? And I do. Okay. So that's the question. So I don't know. Our favorite songs resonate with us, right? And a guitar player plucks a string and they strike a chord and it resonates with the crowd and everyone loves it, right? Waves of light from the sun, they come over the horizon at dawn and you slowly make your way, they make their way into your room and it gets brighter and you start to gradually wake up because the systems in your body are designed to resonate with that light. So resonances happen all the time, all over the place, every single thing, your body, your mind, other things, inanimate objects resonate with things. So that's what we're going to be seeing. We're going to just basically be talking about oscillations, which leads to waves and wave velocities, and then because of waves we have resonances. Okay, so let's get into it. The first types of resonances we're going to see, and the ones that are easiest to work with, are ones derived from simple harmonic motion. And from now on, SHM is the acronym that we're going to use for simple harmonic motion. Here's the thing. Something revolves, we've been talking about revolving things. So here's our wheel, and we'll have it roll this way so it rolls across the page and we can see it. So good. It's got an omega, and it's operating like this. The first thing I want to say is we know omega is angular velocity. The second thing is we know that 2 pi over the period of rotation is the period of rotation, which you guys have intuited over the course of the semester. And to your credit, that's good. So the frequency of an object, F, is how many times it revolves in a certain amount of time. And F is equal to 1 over the period. So if you do the algebra here, then you find that if you do 1 over the period, you really get omega over 2 pi. So, because we could write it as, let's just do it. So 1 over 2 pi is traditionally how it's written, and we'll just do it like that. That is your frequency. This is one of the first things that they used to teach, and now it's all the way up here in chapter 15. So that's fine. You're getting it, and you kind of picked it up already, so good. Let's see, got to move up here a little bit. There we go. All right. Let's talk about units for a second. The SI units for frequency is, it's hertz actually. But that is equal to 1 over a second. And 1 hertz, let's say cycle. 1 hertz is defined as 1 cycle per second. So we've got that out of the way, and we can continue on with the good stuff. So what do we have? We have that circle, and I want to redraw it a little bit better. We'll put this here. And we've got a radius, and I'm going to now attempt to do the difficult part here. Why is it so hard, you say? Well, it's going to be difficult to keep my lines straight. Okay, pretty good. Oh boy, not too bad. Now, all I have to do is draw some sine waves. So, here we go. Oh boy. All right, there's one. And when this is 1, when the cosine is 0, the sine is 1. So we'll come up here, and when the sine is 0, the cosine is -1. We'll get to this point, and then we'll go to this point, and then we'll go to this point. Okay, very great. Okay, so beautiful. All right, so what do we have? We have a curve. We've got this curve, y1, and we've got this curve, y2, and we have a point here that as this thing spins around, oh, I forgot to tell you what this axis is. This is the time axis. As this thing stays in place and rotates around and time goes on, you could think of these as just, there's maybe a pen right here. And this thing spins at a constant omega. And as it spins, this tape gets pulled across and it leaves these wonderful curves. This really isn't a good curve. Okay, so we've got these great curves. So here's 0. And in time. And as we go, we get these curves that map out. And we can say that y1 is equal to some amplitude. This is our amplitude. That's the positive side. Here's the negative side. And y1 is equal to a. And we're going to say it's the cosine of something. We're not 100% sure what yet, so we'll give it a, what should we use for a symbol? I don't know. What's a crazy? I can't use X. I can't use Y. I can't use R or any other thing. Let's use. Can't use eta. We can use eta, I guess. Okay, so we don't know what it is. It's eta times t. And as this thing turns, we're going to pull the string across, and these little guys are going to leave this trail. y2 is equal to also a times the sine of eta, whatever eta is, times t. Okay. It's looking really good, almost as good as the drawing I have on my piece of paper. Not even close. All right. So, A of course is equal to R, because our radius of the circle is R, and when it's pointing straight up, that is nothing but R. So at least we know that. And we know that these are sinusoidal waves. And what else do we need to know? I think that's it. So we're going to move on. This curve has places where we have maximums and we have minimums for the two curves. Oh boy, I didn't do a good job on that one at all. This is where it should be touching. And this is where this one should be touching. And this one didn't turn out so bad. Each of these is pi over 2. So we have that first pi over 2. Now we've got, we're all the way at pi here. This piece is 3 pi over 2, and so forth. Wow, looking great. Drew these too close. Three pi over 2. And did I do that? Did I miss one? Nope, we're back here at 2 pi right here. 2 pi, and then we start in on our new circle. So there's the 2 pi mark. Okay, that's one cycle. So let's rewrite out y1 equals, let's just call it r, since we know that that's what it is, cosine of eta t, and y2 is equal to r sine of eta t. All right, so let's deal with what eta really is. There's a few, this isn't going to be super rigorous. This is more hand wavy. The cosine of 0 is equal to 1, which also equals the cosine of 2 pi. And that's where we start and we stop. So here's the start point, and here's the stop point. And we're saying, okay, great. But if you notice, this is the 0th times 2 pi. This is 1 times 2 pi. And every single time we come back around, we essentially get the cosine of n times 2 pi. So that n is always an integer, starts at 0, n equals 0, 1, 2, blah, 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 all the way up to infinity. Whew, so far, so good. So we know that 2 pi has to fit in here somewhere. Now, and we know that time has to be there. So let's deal with the time part. The ratio of the time over the period has to be some fraction of 2 pi. Must be a fraction of 2 pi. Great. So as t increases, that 2 pi must increase. So we can say that n is equal to that fraction, because it's not necessarily a whole integer, it's a continuous thing. and we're just talking about what it has to be at each point. So n really is t over the period, the time over the period, and that n fraction multiplied by 2 pi, so t over t times 2 pi gives us the right ratio that we're looking for. So let's move this up a little bit. We can now say that if we take this bit and we enter that in as our y1 equals r cosine of 2 pi over t over the period times time, then we have what we need. I don't know if you guys remember, but that is this. Oh, getting jiggy with it. Here we go. That is this. So let's go back down there and we'll write it as r cosine omega t. And that also tells us what y2 is. y2 is equal to r sine omega t. So we have now established that when something rotates, it's giving us a sine omega t and a cosine omega t, or anything in between. In fact, it could be off by a little bit. Let's say that we are really starting at this point here, which means that there's an angle phi that is off, and we'll put that phi in, and we'll talk about phi here in a second a little bit more, but it's really just a phase shift. So y1 is equal to r cosine omega t plus phi. And y2 equals r sine omega t plus phi. Okay, so far so good. What is a good example other than this circle moving around, and we're pulling the cosine and sine out of it? Let's try. We're going to look down on a spring attached to a wall. So we're looking down at it, and at the end of the spring we have this mass, and there's an equilibrium point right here, x naught, and the box then goes back and forth between this point and this point. So if we say this way is positive x, then this would be our positive amplitude. Here's x max. Here's our negative amplitude. Okay. We again get our sine and cosine out of this. All the concentration in my body went into doing that. And let's see how I did. Here's our initial sine. This should be a peak when that is down. This should be a peak when that is down. Not too bad. Did we get... yep, there's our peak. So here's our 2 pi peak. 2 pi. Here's 0. All right. So this guy bounces back and forth between the top and the bottom. And I've got two things here. We've got y1, which is the actual position, x of t is equal to, where did we say it? Did we say a equals x max? Our a is our amplitude, by the way, for anyone, amplitude. So our amplitude is x max, and we've got the position as the cosine of omega t. I'm going to leave off the phase. Okay, we're just going to leave it like that. So great. Everything's going swimmingly. Our time goes from this time equals 0 to omega t equals 2 pi. So whatever it takes for omega t to equal 2 pi at this point, for t, for whatever t needs to do to make 2 pi happen at this point, that's what has to happen. And that really doesn't matter a whole bunch, because we're drawing it out according to what we've got defined. So that's it. The phase shift. Should we talk about the phase shift? Okay. The phase shift, real quick. If we were to subtract or add to the argument, when you add inside the argument, you're really subtracting. I know, it doesn't make sense. So if we were to say the sine of omega t plus pi over 2, so we're basically saying our phase shift phi is equal to pi over 2, then if we do this point, they're supposed to be in line with each other. This point of pi over 2, if omega t is equal to pi over 2, and this is equal to pi over 2, then we're really getting the sine of pi, which is 0. And when you shift this, that's what you get, the sine of pi. So that's what the phase shift does, and it puts you on a trajectory just like the cosine. So depending on your phi, of course, because the cosine and the sine are out of phase by pi over 2. So that's what a phase does for us. It will transform, if you use pi over 2, it can transform your sine to a cosine or vice versa. Or if you're not doing, if you're actually off by maybe 10 degrees or 0.32 radians or something like that, that phase shift will be there for you. And you can just work with it. It's okay. I'll show you why in a second. You don't really have to worry about it. In fact, you can just zero everything out and get rid of the phase shift if you want, and you should. So, we're going to go to talk about the position. X of t, the velocity v of t, which equals dx of t dt, and the acceleration a of t, and that's dv of t dt. And we already said what x of t is equal to. I'm going to go back to using a instead of x max, because x max gets complicated. So there's too many x's if we keep x max in the system. So we're going to use a. So x of t is equal to a cosine omega t. If we take the derivative of that, we get v of t is equal to minus I'll do it, sine of omega t times omega, because you have to take the derivative of the inside as well. So let's write it neater right here, minus a omega sine omega t. The derivative of omega t is equal to omega. So that's where you got to do the chain rule thing. Very nice. And we do it one more time, and we get negative a omega squared cosine, back to cosine, omega t for a of t. So that's our position, our velocity, and our acceleration for this device. And we can see how our velocity is the sine of omega t, so that's our sine curve, and our position is the cosine, and our acceleration is also the cosine. So the only differences are their absolute amplitudes. That's the only difference. These are important, hugely important. So I'm going to box it all in. So you hopefully will write that down neater than I have. And like we talked about, you can slap in each of those, you can slap your phase in there. And what happens? When you do the phase, you're still taking the cosine and turning it to the sine, negative the sine. And then the sine goes to the cosine and all that as you're doing your derivatives. When you do d of the argument, dt, like we did up here, you still get omega because d of dt of this thing here doesn't mean anything. It's a constant, so that doesn't matter, and you still end up with omega. So having the phi in your argument, this is what they call the argument. When that's in the argument, it doesn't matter. So you can keep track of it. It's good to know if you need it. If you're doing an experiment and you have a phi offset, then you keep it. But it falls out, and you can pretend that it doesn't exist most of the time. And probably any questions I'm going to ask you won't have one. So we're lucky there. And I just want everybody to realize that we're dealing in this situation with Hooke's law. And we're going to stay with that for a while because it's such a good use of this is essentially where all these things came from anyway. So we're going to learn a little bit about this. All right, so we've got Hooke's law. So what is Hooke's law? F equals minus kx, which also happens to equal ma. So convenient for us. A then equals minus kx over m. All right, let's keep that in mind. What if we stick a of t and minus kx of t over m, like that? Interesting. What are we going to do? Let's do it. Let's continue on. We've got minus k over m, and we're going to put in x of t, which would be a cosine omega t. So far, so good. Now let's do the a part. A equals minus a omega squared cosine of omega t. Well, this piece equals this piece. This little a equals that a. So I'm just going to start canceling out things that are equal to each other. The negative sign for one. That leaves us with k over m equals omega squared. which gives us omega equals k over m square root. How about that? Very nice. All from this Hooke's law and this definition of the positions. So we've got all of that, and it's just snowballing all the cool things that are coming out of this. So we've got omega equals k over m. One thing done. The period is equal to 2 pi over omega. So we're going to say 2 pi. 1 over omega would be m over k. So we've got t equals 2 pi m over k. Are you guys thinking about this? You're usually given a mass, right? So the mass is given to you. The spring constant is given to you. So all you need to do is divide the spring constant by the mass and take the square root, and you have your omega for the system. How about that? Nice, right? So good. You can get the period the same way. The period of revolutions for this thing is the same right here. M over k square root, and you've got your period. So it's weird that the mass and the spring constant are really all you need to come up with your oscillation velocity and the period, or the period of rotations, which also leads us to the frequency, which is 1 over t. So our frequency is equal to 1 over 2 pi k over m square root, which also happens to equal 1 over 2 pi times omega, as it should. Okay, hope nobody has questions on any of that, but all of that is really, really good stuff. And we're going to start now talking about the energy in the system. And we know that energy in simple harmonic motion we're still dealing with Hooke's law, so F equals minus kx. And of course, work is equal to the force times the distance. And that leads us to, of course, we're going to consider all this in the x direction. So dw is equal to f dx. And taking the integrals of dw gives us w for work. And that equals the integral. Let's get rid of that. F dx. And of course, we're going to go from x naught to x max, but x naught equals 0. So now let's introduce our minus kx here. So 0 to x max. Our f is minus kx, so kx dx. So our work is equal to minus 1/2 kx squared from 0 to x max. And we'll do that, and we end up with minus 1/2 kx max squared. So the work done is this, but we also know that the potential energy, PE, which equals U for a spring, is equal to 1/2 kx squared. And in our case, we're at the maximum, so we're going to say x max. That potential energy is what was stored in the spring. So the work that it does is the opposite. So the work is equal to minus delta U. We didn't have the 0 part. I used x not equals 0 instead of leaving it as just a regular x. At any rate, it's minus delta U, which means that your potential energy is stored as a positive. The work of the spring ends up is giving away the energy. So you're storing the energy in the system, you're giving it back away later, and that is the work done by the spring. Okay. So our total energy, or energy maximum, should be 1/2 kx max squared. Okay, so far so good. Okay. Energy total, in general, our energy total is equal to our kinetic energy plus our potential energy. And in general, our kinetic energy is 1/2 mv squared, and our potential energy in the case of a spring is 1/2 kx squared. Not x max, just x. Whatever the x happens to be somewhere along the line. So that is our energy total. And we can then introduce our position, velocity, and acceleration in terms of in time. So E in time is equal to 1/2 mvt squared plus 1/2 kx of t squared. And I'm actually going to switch these around. So we have the x first and then the y. Or excuse me, the x and then the velocity. So that's fine, but let's raise this up a little bit. And let's begin. So E of t is equal to 1/2 k, and then x of t is squared, of course, But x of t is what? What did we say x of t is? I can't remember. Somebody help me. You guys can't help me. I'm too far. I've gone too far. Okay. A. Cosine omega t. And we're squaring that. And we are going to add 1/2 m. We're going to do a minus sign for the v. Omega sine of omega t squared. I think that's right. Okay. Now, here's where the book does something really cool. They go and they show that E of t is really just E, and that E is equal to, if you use a bunch of stuff, you have to use, you can do this for yourself or you can look it up in the book. It's in section 15.2. So go to section 15.2 and you can watch them do this thing, because omega equals k over m square root. Do I have that right? K over m square root? Yeah. That's got to be right. Okay, so they use that, and then they use cosine squared plus sine squared equals 1, and some other stuff. I think that's it. I think they just use those two things, and they show that the E is equal to 1/2 k x max squared. Okay, well, we already knew that. What we didn't know was that E is constantly that. So it doesn't matter. It's a constant. E can't be conserved if it changes. If it changes at all, it can't be conserved. So the conservation of energy would be totally thrown out the window. So E must be, as a function of time, it must be constant. So what does that mean? The derivative of E of t with respect to time must be 0. This, the book shows you this, and that's great. What we're going to do is we're going to see this. Let's go right there so we can see it. I don't like how that always pushes over at the very last second. Why are you moving around like that? All right. So here we go. We're going to use this equation, and we're going to do the derivative of E of t with respect to t. And it's not terrible. First of all, when you take this function here and whatever that is, that's where our t is. So we've got this squared part. That squared part's going to drop down, get rid of this 1/2, and we're going to be left with k times a times cosine of omega t and we're going to multiply by the derivative of the inside of that thing, and that is minus a omega sine of omega t. Okay, one in the box. Now we're going to add the next derivative. We get rid of the 2. We bring that down. We left with m. And we've got our -1. We've got our a. We've got omega. And the sine of omega t. Yeah. Technically, we should probably have another omega out front, because in the end, I'm going to stick a little omega in there, and I'm going to put a squared on that one. And because in the end, we end up with another -a omega squared. No, I did it right the first time. We don't want that, and we don't want that. And that is omega squared times the cosine of omega t. Right, so far so good. So d of e t dt is equal to, hopefully, 0. That's what we're hoping for. Let's find out. This piece has a negative here and a negative here, which are going to cancel out and give us positives. So let's write that one first. M a squared omega cubed, and that will be the sine of omega t times the cosine of omega t. Then this one has just one negative sign, so we're going to leave that. We have k a squared 1 omega times the cosine of omega t times the sine of omega t. All right. So far, so good. This piece and this piece are equal. So we can factor those out. If it is 0, we can set this section equal to that section. And if this piece is gone and this piece is gone, then here, let's get rid of that negative sign. Then we can just write out m a squared omega cubed, is it equal to k a squared omega? Well, the a squareds can go. This one omega can go, and then that leaves us with 2. So omega squared. And hopefully omega squared will equal k over m. Is that true? Yes, it is true. So d of et equals 0. And it should. All right. So it equals 0. Great. Everything is fabulous. And we already know that the E is equal to 1/2 k x max squared. Okay. And it's constant. So that ends this first section. I will have another lecture tomorrow to post, and this is the beginning of our chapter 15, Oscillations. Chapter. Okay, see you guys.